This video is about the singular value decomposition, but let's first recap a little bit some other decomposition. So we have the QR factorization, which is, so it decomposes the matrix A into two matrices, so Q, which is an orthogonal matrix, and R, which is an upper triangular matrix. And then we have the variation of the QR factorization called the CPQR, column pivoted QR factorization, which is essentially the same, but where you perturb the columns of A, and this is done in order to obtain better low rank approximation properties. This video is mainly about the singular value decomposition, which is it involves decomposing your A matrix into a product of U, sigma, and V transpose, where U and V are orthogonal matrices, and sigma is, well, it's essentially a diagonal matrix. Okay, later we're going to also cover a decomposition called the CUR decomposition. This is the singular value decomposition theorem. So it's an existence theorem. It illustrates that there always exists a singular value decomposition. So for any matrix A, you can always decompose it into three matrices, U, sigma, and V transpose. So U and V are so in this version of the factorization, they are square matrices. So U has the same number of rows as columns, and V has the same number of rows as columns. And so that's the full version when they are both square matrices. Okay, since U and V can have different size, sigma must be a rectangular matrix, and the diagonal rectangular matrix, and it can look like this or like this depending on which dimension is larger. And in the singular value decomposition existence theorem here, you also assume that the singular values are ordered, and they are ordered in decreasing magnitude. So the singular values, which are, so it's the diagonal elements of the sigma matrix, they are ordered by non-increasing order, right? So the sigma 1 will always be the largest singular value. Let's list a couple of properties of the singular value decomposition. The first two properties are related to how you can compute the singular values. And so the singular values are equal to the square root of the eigenvalues of this matrix here, A transpose A. Property 2 states that a subset of the eigenvalues of this matrix, 0A, A transpose 0, are the singular values. There are some other eigenvalues which are not the singular values, so essentially, a subset of the eigenvalues of this matrix are the singular values, and this is how this property is used in algorithms for the singular value decomposition. So, for example, the SVD command in MATLAB essentially computes the eigenvalues of this matrix using a structured version of what's called the QR algorithm. Okay, that was about how to compute the singular values. The singular value decomposition can be used for a number of different things. So you can use it to compute the norm of a matrix. So yeah, and that's how it's used in many standard mathematical software tools. So in norm command in MATLAB, it computes the SVD and returns the largest singular value. You can also compute the norm of the inverse of a matrix, which is, so it's related to it's the reciprocal smallest singular value. These combined is the way that you compute the condition number of a matrix in MATLAB again. Okay, and you can also use the singular value decomposition to compute the solution to a linear least squares problem. Yeah, so we already saw how the QR factorization can be used to solve a linear least squares problem, but you can also use the SVD. And on the left-hand side, you have the linear least squares problem, and on the right here, you have also a linear least squares problem, but involving diagonal matrices. So the sigma matrix is diagonal, so that allows us to solve the system on the right hand side directly. And then finally the Echad-Young theorem. And so this is the most important property of the singular value decomposition, and that's that the problem to find the best low rank approximation can be explicitly computed with the singular value decomposition. So on the left hand side here you have an optimization problem where you have a given matrix A, and you're trying to find another matrix X which has a given rank, so rank K. So this tries to find the closest matrix which has rank K. So you are given a matrix A, and then this optimization problem involves sort of trying to find a nearby matrix which has rank K. And this is the SVD can be used to directly write down the explicit solution to this problem, and it's given by this right hand side here, which is it's a sum involving things contained in the singular value decomposition. But more about that in the next video.